We're starting our fourth help video on 5-11, Unit 5's test. Picking up with question 24. Nitrogen has a higher ionization than oxygen. In fact, nitrogen's 1400, oxygen's 1310. And that does not follow the trend. The trend says ionization energy should increase left to right because the atoms are getting smaller. 800, 1090 is higher, 1400 is higher than 1090. Then it drops to 1310. Then it goes up to 1680, so it's back to going up, and then 2080. So it's going up left to right here, except between nitrogen and oxygen. Why? It says, which of the following statements explain why? Ionization energy tends to decrease left to right. No. It tends to increase left to right, so that doesn't explain it. Oxygen has a lower shielding effect than nitrogen. Shielding effect is when inner levels block the pull of the nucleus on electrons on the outermost level. Well, both nitrogen and oxygen are on the same level, so they have the same shielding effect. They each have virtually no shielding effect because the only level they have inside the second level is the first level, which only has the S sublevel. That's not much of a shielding effect. There's only 2 electrons on the inside level for both nitrogen and oxygen. Oxygen has a smaller radius than nitrogen, which resulted in having a lower ionization energy. Well, if oxygen does in fact have a smaller radius than nitrogen, and it does, they're very close, it would actually give it a higher ionization energy because the smaller you are, the higher the ionization energy is. So A, B, and C don't explain. Oxygen has a higher shielding effect than nitrogen. No, they have the same shielding effect. They have the same shielding effect, not higher. And letter E, we're hoping that one's right. Nitrogen's electron configuration is 1s2, 2s2, 2p3. Well, let's look. Here's nitrogen right here. 1s2, 2s2, 2p3. Here's oxygen right here. 1s2, 2s2, 2p4. So what do these configurations mean? If you remember, configuration has something to do with ionization energy, and we said we would get to that. One of our previous questions, 21, which affects ionization energy? The configurations can affect it. And this is a case where the configurations affect it. Oxygen's configuration has 4 in the 2p, which means that if we look at oxygen, this electron, this 4th electron, is paired up. So when we go to try to pull that electron, this one's negative and this one's negative. This one is going to help push that electron out. It's going to help push it out because negative repels, which would contribute to it having a lower ionization energy. Letter E is correct. What about AB? Oxygen has a larger radius. Actually, it doesn't. It has a smaller radius. Ionization energy decreases left to right. No, it increases. Oxygen has a lower nuclear charge. No, it has a higher nuclear charge. Oxygen has 8 protons. Nitrogen only has 7. So those are all not helpful explanations. Okay, on this question, 25, they want us to place these elements in these boxes in order from smallest to largest. So we're looking for the smallest one first. We know that size gets bigger as we go top to bottom, so 3 and 4 certainly are not going to be the smallest. We know it gets smaller as we go left to right. We know it gets smaller as we go left to right. So number 1 can't be the smallest. Number 2 has to be the smallest because it's the highest up on the table and it's to the right on the table. So number 2's got to be first. That would get rid of answer B, C, and AB. Those answers we could get rid of. So our smallest one is number 2. Then we continue to the left where they're going to get bigger, and we come to number 1. Number 1 should be the second smallest. So we're looking for 2 first and 1 second. 2 first and 1 second. Letter A's 2 first, 1 second. Letter D's 2 first, 1 second. And if you look at letter A, it has the same answer as letter D. And then this one has 2 1s, so we can't eliminate anymore. So now we've got to figure out. They're getting, as we go top to the bottom, they get larger. So number 4 is bigger than number 1 because it has 2 more levels than number 1 does. but it's to the right of number 3. So they get smaller left to right, so number 4 should be third, and number 3 should be the largest out of all of them. So it should go 2, 1, 4, 3. The only answer that's 2, 1, 4, 3 appears to be letter E. All right, we continue on. Now we need to match the elements to their electronegativities, and we have to figure out who would have which of these numbers. First of all, looking at the elements, we have sodium, carbon, bromine, and beryllium. So we have bromine, we have sodium, we have carbon right here, and we have beryllium right there. We could kind of look at size a little bit. Bromine's furthest to the right, but I'm looking at bromine right here, and bromine is in family 17. Family 17, group 7, the halogens. Bromine only needs 1 electron to become like krypton. Bromine needs 1 electron to become like krypton, satisfying the octet rule. It's S2P5. If it gets 1 electron, it would become S2P6. That satisfies the octet rule. Bromine should have the highest out of all those because it's the only one that's a halogen. It's the only one that can satisfy the octet rule. Letter A would be bromine. We continue on. They get smaller as we move left to right in general. We look at these particular elements. Look at carbon. Carbon's going to be very small compared to all these other ones. So it should have a relatively high electron affinity because the smaller you are, the better you are at pulling the electron to you, and the more likely you need that electron. If we look at carbon, it's in the second column of the P. If carbon can get 1 more electron, it becomes a P3. A half-filled P is better than a not half-filled P. So carbon can benefit by the addition of an electron. If we look, sodium is bigger than carbon. It's to the left of carbon and a row beneath it. So sodium is not going to do as well by getting the electron as would carbon. So carbon has the highest electron affinity, the second highest electron affinity overall, and the highest of the elements remaining. Carbon would be letter B. Now, who would want 1 more, sodium or beryllium? If sodium gets 1 more, it's S1, it becomes S2, we could fill the S. We learned in our rules that a half-filled P, D, and F or a completely filled S, P, D, F offers some stability in the factors that contribute to electronegativity. In fact, we look at a question coming up a little bit later on the test. And it deals with which factors influence. It's the very last question on the test. Which factors influence electronegativity? Factor 3. In this case, letter C. Stability of electron configurations. A half-filled P, D, or F offers some stability, which means they would have a higher affinity. A completely filled SP and DF also offers some stability. So if you can completely fill the SP, D, or F, they would tend to want that electron. So if sodium gets an electron, it will help it a little bit. It's to the left of carbon and down a row, so it's bigger than carbon, so its size is not going to attract the electron to it as well, but it would want it some. It would be a minus 54.8, letter C. But what about beryllium? Beryllium's already an S2. And an S2, we said, offered some stability. If you give beryllium an electron, it would go from being S2 to S2P1. The P sublevel takes energy to open. The P sublevel has more energy than the S. If you remember, the energy of the S sublevel is 0, and you would add it to the energy level, E equals N plus L. The energy of the P, we assigned a sublevel energy of 1. So the P takes more energy than S. If it was, for instance, beryllium's on the second level, the 2P would have an energy of 3. So it would be putting the electron in a higher energy sublevel, requiring it to add more energy to get it to take it, we would really ruin beryllium stability. When the stability goes down, we have to add energy to it. It's always a trade-off. When stability goes down, you have to add energy. If stability goes up, then that side of the teeter-totter would go down. So beryllium would actually have a positive affinity, but in this case, 0 means it doesn't have an affinity for that electron. Number 30, which statement is false regarding affinity? Can affinity be negative? Yes, if you improve stability, it is negative. If stability goes up, the energy side of the teeter-totter can go down. If stability goes up, this side goes up. If that side of the teeter-totter goes up, then the other side of the teeter-totter energy would go down. That means it's released. That means it's negative value. Letter B, in general terms, affinity follows the trend of ionization energy. That is true. The elements on the right side of the table benefit more by the addition of the electrons overall. Why? They're smaller. They can hold it to it, pull on it better and accept it. Plus, if the ones on the right side get an electron, they go closer to satisfying the octet rule. Letter C, ionization energy is always a positive number. Absolutely. Ionization energy is the energy it takes to remove an electron. It always takes energy to remove an electron. Ionization values are always positive. You have to add energy to the atom to remove its electron. Letter D, when the atom loses stability, the atom must also lose energy. Oh, no, 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 no. When he loses stability, the energy side must go up. It must gain energy. When stability goes down, the energy goes off. That's the stability energy teeter-totter. When stability goes down, the energy side goes up. You have to add energy to the atom to get it to take it. That would be endothermic. Which of the following best explains why magnesium has an affinity that's often listed as 0, meaning it has no affinity to the electron, but it can also be listed as a positive number because we have to add energy to magnesium. Well, if we have to add energy to magnesium to take the electron, if we have to add energy to get magnesium to take it, it must mean magnesium stability goes down. Why would magnesium stability goes down? For the same reason that beryllium did. Magnesium and beryllium are both S2s. To get them to take an electron, you have to open the P sublevel, which has higher energy than the S did. So you ruined its stability by giving it an electron. Letter D, magnesium's S2. Well, how do I know that? Because magnesium is in the second column. There's magnesium. It's S2. And we ruin it being S2 by giving it an electron. It takes energy to open the P sublevel, as it tells us right here. Energy is the N plus L. The energy of the 3s, when you're in the S, your second number is a 0. 3 plus 0 is 3. The energy of the 3p, when you're in the P, your energy is 1. The 3p would be 3 plus 1, that's 4. The 3p has higher energy than the 3s. So you're adding energy to a higher energy sublevel. You have to add a higher energy. It's going to result in adding energy in. It's going to be greater than 0. When we pick up on the next video, we will start with question 32.